So, good morning. Welcome to Krishna's classroom. Let's continue with our discussion on the measure and measurable sets. We started with the objective of extending the concept of length that is defined for intervals to a function that shares all the properties of the length function to a larger collection of subsets of R. Now, with this objective, our strategy was to define something called an outer measure. So, we introduced the concept of outer measure M star. Outer measure is an extension of the length concept. To all subsets of however, it is subadditive and does not have the countable additivity property. In fact, we have seen that one of the crucial properties or desirable properties or indispensable properties that the length function should have is the countable additivity property. So what we could do was extend the concept of length to all subsets of R. However, this extension did not meet the crucial requirement, namely that it is countably additive. We have discussed these things in detail. However, we had all the other nice properties that we had M star of E plus x equal to M star of x, that is, it is E star of E, that is translation invariance. This is translation which of course your length function or the concept of a length for intervals, right? Then it failed to meet the countable additivity property, and of course, as I said, it was an extension. So M star of interval equal to length of interval I and interval So this is So it has only partially met our requirement. Then the next stage was we introduced the concept of measurability. Measurable 6. So the problem was this: insisted on all the three desirable features, namely countable additivity, translation invariance, and the fact that measure is an extension of the length concept, we fail to to have all subsets of R coming under this function. That is a problem. So M star failed to have countable additivity. So when we picked sets for which countable additivity is true for M star, then what happened was we were not sure whether it is true for all subsets of R, at least. Not on every M is different. So For all these three features coming together, we had to possibly sacrifice the luxury of the measure defined on all subsets. Now, this is still a question. We have not explored it yet. Okay? Whether this is true or not, or is it true that M is defined for all subsets of R. So, the first question that we raise at this stage is this. Defined for all subsets of this is the first question that we are raising. See, one thing that we had was that, recall that the collection of on which M star is a measure countable additivity problem. Is a rich class. Having all borrow sets. That means all open sets are there, all closed sets are there. Then the smallest sigma algebra that contains open sets is a subcollection on which M star is equal to M. So that's so it is already big enough. I don't think we require it to be. I mean, if it's nice, if it is defined for the whole of all the subsets, but if not, we are already satisfied with its stature, namely that is defined on a large class of sets. So we try to answer this question. Okay. So we explore this question. Measurability of all subsets of and we end up constructing a non-measurable set. In the sense of Lebesgue, So recall that all sets of measure 0 or outer measure 0 are measurable. So recall that all subsets of outer measure zero are is what you have. If where E belonging to measurable. This is the outcome. And for such sets, m star of E equal to mb, which is equal to 0. Okay. A simple inference. Every subset of set of measure 0 is also measurable is also measurable. And obviously that is A is these results we have proved. Okay, right. So the search for non-measurable sets is only is now confined to sets of measure not equal to 0 or sets of outer measure not. Okay, so let us start with this. Before that, before we prove this, we construct or work out some tools for it. Okay, so let us prove some lemmas. So we prove some results which are useful in our investigation. Let R be one, E is measurable, E is measurable, 2, E is bounded, 3, lambda is a countable bounded subset of R. Something like all rational numbers on the interval 0 to 1. Okay. And fourth property is that E plus lambda, that is the translate of this for lambda belonging to collection, is a disjoint then what you have is this. So that's a lemma that here. So the conditions are E is a subset of R, E is a measurable set, E is a bounded measurable set, lambda is a countable bounded subset of R, and the collection E plus lambda, this is a translate of E through lambda, is a disjoint collection of subsets of R, then measure of C. Okay, let us prove this. Because we will be using this result in constructing the non-measurable set. Okay. So what we have is this E plus lambda disjoint collection of it's also, you see, if E is in M, E plus lambda is in M. Therefore, I am using this. Okay. So, you can write here. That's not obvious. Then, what we have is this measure of union E plus lambda is equal to, because of the additivity property of M on script M, this is equal to sigma measure of lambda. This is equal to Measure of E plus lambda is equal to measure of E. So this is sigma, lambda belongs to lambda, measure of E. That means measure of E added countably many times. Okay, right? This is because measure of now what we conclude from this is that the measure of E is necessarily 0. Now we observe that is bounded. It is bounded. And of course, is finite. Okay. Now suppose measure of E is means it is measure of is not equal to 0. Then we have the following. What is that? You have from this relation, see that the RHS of star is a countable sum positive terms. It's not convergent, obviously not convergent. Because summation over it's a countable sum of 1. Okay, right? And therefore this is equal to infinity. Okay. So what you have on the other hand, the left hand side is a finite, finite. Because this side it is finite, on this side it is infinite, and there is equality. So that's a contradiction. Hence, measure of E is equal to 0. So that completes the proof of that. So we shall use this result somewhere. Okay, where we shall use it, you will see soon. It comes very handy in the construction of the non-measurable set. Now we start with do some preliminary work. So let E be an arbitrary set and E now define the following relation. On E, that is x belonging to E, y belonging to E, x is related to y if and only if x minus y equal to R. We say that two elements x and y of E are related if their difference is a rational. Okay, so this is the relation there. Now it's easily seen that this is an equivalence relation. That is obvious because x is related to x is related to y, means y is related to x. One, trivial. It is trivial to prove that this is an equivalence. But what does this do? So this induces a partition of it partitions E into equivalence classes. That is, E is now the union of x belonging to E bracket x. Now I will define what these sets are. That is the connection. So each block consists of all those y, or the block x consists of all those y which are related. Okay, so it's a union of this collection. Then this is possible because what happens, you see that is either equal to or empty. So this is the property that you have. Either these are equal for x and y, x is equal to y, or x is intersection, the collection equivalent to x and the collection equivalent to y, the intersection is, I mean, this is quite easy to prove. Suppose then it's not equal to empty, or assume and of course this condition is, suppose this is not equal, then there exists z belonging to, and that means z minus x some r1 belonging to z minus y r2 okay. Therefore this together would imply that you can easily work out. If you subtract, okay, then you get y minus x into some rational number done by these two, the difference of r1 and r2. Okay. Which implies that's a contradiction. It implies this. Therefore, we see that the only possibility is, hence we have either or so that we have proved. So that is the partition that we have. Now let me just say what we do next. So we construct what is called the so-called choice as follows. See, this is what you have. See, this is your E. E is now partitioned to, so this is Y, this is some Z, so to define CE, the choice set, to be the collection of all x belonging to with the property that x belongs to exactly one of the rational equivalence classes associated. We shall say that this is what is called the rationally related classes. Okay, what does it mean? It means pick x1 belonging to x, y1 belonging to y, z1 belonging to exactly, and etc. and so on. So you have all the classes. Okay? So pick from this is x1, this is y1, this is z. Okay, and so on. So this collection exists by axiom of choice. Such a choice set can be expected. One can construct a new set, a set consisting of exactly one element from each of the classes. So in general, what you are going to get would be a, see, what we are eventually going to do is we start with a E with a positive outer measure. What does it mean? It cannot be a countable collection. It's an uncountable. Therefore, when you build this kind of equivalence classes, then you see how many such elements are there. It is again uncountable. So the set that you have constructed C now has uncountable elements constructed under this condition, and the axiom of choice supports or justifies the existence of C. That's what it is. Okay. Then we have the following. Following properties. First one, x belonging to C, y belonging to C, x not equal to y implies there does not exist x minus y does not belong to Q. It's not rational. That is the first property. The second property is that for each x belonging to E, there exists exactly one C such that x minus C is a rational Q. So what it means is this. Suppose you take an x belonging to, so x belongs to one of these blocks. Okay. Then there is some C belonging to C, because C we have constructed by picking one element from each of this. Okay. So certainly there is one element which shares the same class with the x, and that is C. Okay. So there is exactly one C belonging to C such that x minus C is equal to Q belonging to Q. That is this is the meaning. So we have seen the construction of C. Okay. Now further, for lambda belonging to is why is it so? So you take say lambda 1, lambda is okay. So let us see this. What happens? Suppose this is not then there exists comma lambda 2 belonging to lambda such that no. That means there is a common element between them. Okay. So let What does it mean? That means C is equal to which is also equal to x2. Okay, right? What would this mean? Where of course lambda 1 belong to Q lambda and C. What does it mean? Means x2. x1 is related to x2. This is the point. There's two elements unless they are equal. Okay? Unless they are equal. See, this is going to be the. So that's a contradiction. Therefore, what we observe is that the lambda plus C is a disjoint collection. So that completes the proof. Okay, so this is a disjoint. What is the consequence of that? The consequence of that is this. That is, what does it mean? Means m star of C has to be equal to 0. From what we have proved earlier. Okay, so let us now prove it. This is Vitalis theorem. This theorem proves the existence of a non-measurable set. In fact, it is a very constructive proof. It's not a something where you prove the existence by fault or something like that. But you see, actually we have constructed C and we show that C is not measurable. Set E of positive outer measure contains a non-measurable set. So So the condition that we ask for is this, that E is contained in R with a positive outer measure. Okay. So by the countable subadditivity of the outer measure M star, by the countable subadditivity of the outer measure M star, we may assume E is bounded, E is bounded. So construct C choice set chosen with the rational equivalence relation. That means you remember the sets that are involved are the partition class. There's a partition, okay, and we are picking from each of these a single element. Construct this C, and the equivalence relation is connected with the rational numbers. That means we say that x is related to y, x minus y is a rational. So what we prove is this. This is what we have. Because here we take lambda to be a countable bounded subcollection of so what we have is this. We have M star of C. This is equal to okay. We have to make the crucial assumption. Assume. Then what we have is this. m star of because we have assumed that C is measurable, and this is less than or equal to m star of E, and this is less than infinity because we have chosen E to be bounded. That is, since E is bounded. Okay. Now what you have is this CE plus lambda for lambda belonging to lambda naught that of course is a collection of translates of C. First we take lambda naught C a phantom. For example, lambda naught you take all rational numbers in a bounded interval. That's the example. So let us work on this. Use this. You see that by the lemma see. No, we want to arrive at a contradiction. So how do we see? Now we contradict this. So this we know is stemming out of this particular property. We try to obtain contradiction. By choosing since E is bounded, there exists B positive such that E is contained in the interval closed interval minus B. Now choose that means all rational numbers enclosed in the closed interval minus 2b to 2b. So you know that this is a countable collection. Lambda naught is a countable collection. Now we observe the force. Then lambda naught is bounded and countable. Also, so bounded. So we already know that the measure of CE has to be equal to 0. So we are going to contradict this. Okay. For that, now E is claimed is contained in Q. How do you prove this? See that, suppose you take two elements here. Okay, right. If X belongs to E, then we show that X belongs to lambda plus C for some lambda, and lambda naught, where lambda naught is of course minus 2d. Okay. So what does this mean? This means the following, that is X is in E means X is in some equivalence class containing X. So X belongs to E class containing such that some dimension belonging to Q. Okay. Now we claim that so all that you need prove is this. Okay. So note that mod x1, and you see that these are elements in E, therefore you see that this is less than or equal to, which implies lambda 1 belongs to So what happens is that every x in E is in one of these lambda plus series. Now we can easily get the coefficient. It's easy to construct a contradiction. X belongs to the union of C. Therefore, E is therefore what you have is this. See, if you look at the M star, do not assume E is measurable or anything. M star of E is less than or equal to sigma M star of lambda plus C is M star of C. And what do you have here? This is equal to and M of C equal to 0, and this is equal to 0. Okay, right? This is what since M of C is equal to 0. But what do you get? So you get we have assumed M star of E is strictly positive. This is our assumption on the choice of so we have started with a set of positive measures. So this is what we have 0 less than M star of E less than E. This is what we have chosen. This is the choice set. Okay. Hence this contradicts more view. Two things: C is measurable, and consequently because of all other conditions equal to 0. Therefore, what is the possibility? Therefore, the two statements is C naught. So the important point is this, that we started the bounded set. Started in, I am using Venn diagram. E is a bounded set. Okay. Now we used all rational numbers so what I had was this. See, E is bound. E is, lying inside A is a subset of the rho. Okay. Now what we do is choose a lambda. Choose an interval I is equal to minus 2p. Okay. So you see that this is I minus b, and now if you try to translate E through a rational number here, okay, so then we will drop this. So this is not right. So what you can prove is that there exists some lambda in lambda naught with the property that this is what you have is this. E is every element of this is in the translator C using that. Okay. Right. And therefore you see that eventually we obtained from the disjointness of this class measure of C equal to 0, and that contradicts our assumption that m star of E is positive. Okay. Therefore this is correct. So there exists a non-measurable set, right? So that proves one of the crucial theorems that the consequence is very fascinating. Remark. This M is properly in fact, what is more fascinating is that now a corollary is the following. With a positive outer measure, has a subset which is not measurable. It shows that there are plenty of Kumar, non-measurable sets. Nevertheless, what we have shown earlier is that almost all the desirable class of subsets having some nice properties is a measurable set. Still, we have a remarkably huge class of namely script M, that is a measurable class containing all desirable so that's the thing. So what we have proved now is that this is not a that the script M or the measurable collection is not the set of all subsets of R. Okay. So that is, so we have settled the question. And now what we need is, what we also prove is another little result which follows easily in the next theorem. There are disjoint such that m star of now we know that this is in general. Now we show that give a contradiction. So now what we do is we simply apply the definition of measurability. We have any E and now you see that since C intersection what does this mean? This implies That means he is measurable. So if thus we obtain all subsets are this contradicts the existence of this A comma B that comes. So I think we will stop at this stage, right? So we have proved an important result, namely that there exists non-measurable sets. That means the class of all measurable sets is not as large as the set of all subsets. Thank you very much.